So we will continue. With our discussion on growth of density fluctuations. So yesterday we focused mainly on dark matter, and today we shall study baryonic matter, which has pressure support. But before going into the study of baryons, let's do one thing. Let's try to understand how these fluctuations look when we go to Fourier space. So this is a convenient and very useful technique. So we shall see why it is useful. So Fourier description. So we have this overdensity delta x t that we spoke about yesterday. And now what we shall do is we shall look at delta, which is what we denote the Fourier transform as k t. And this is 1 by, we'll use this definition of Fourier transform. All right. So this is also the standard definition of Fourier transform. But what we're really looking at now, this overdensity field, this is some random field. First of all, this Fourier transform is in X. Now we haven't spoken much about the X dependence of these fluctuations in the last lecture, but today we shall have a lot of discussion in the later half of the day. So we'll speak about what kind of objects this delta are as a function of X. So we predominantly spoke about the function of T. So in fact, we can split it here. So we can write this as some delta of X, and as we wrote, d of T. So we are essentially looking at the Fourier transform of this delta X. Now, what kind of a object is, what kind of function is this? So as we shall see that these are basically random. So if you plot it, imagine this is in 1D. So you have some sort of a density, over density field. Okay. So as a function of X. So let's just see it in 1D. Now, what we are really doing, and is of fluctuations, right? And let's just, for simplicity, assume it's a one-dimensional thing. Now, what we are essentially doing when we are doing this Fourier transform is we are looking at this function delta X and resolving it into modes, right? So we are resolving it into waves of different wavelengths. So we are adding different waves, and each has a different amplitude. And this amplitude is what we call delta of K. So for each of these wave numbers, you have different amplitudes, and you sum them and you get this. So that's roughly the idea of this thing. Now, what happens in linear theory is that when you break this complicated density profile, this overdensity field, into these modes, they don't couple. So in the equations that you have, these modes, they grow independently of one another. So that is actually something which it's like, if you have remembered that when you have coupled oscillators, then you usually go to normal modes, and that's basically what we're doing. So when you go to these modes, your system becomes decoupled. So the reason why we work with these this Fourier space is because in linear theory, the modes get decoupled, and it's much convenient to work. So let's just write down the standard quantities in Fourier space. So for example, we already saw that you have this definition of delta K and T, which is the Fourier transform of your overdensity field. And this is like d of T and then some delta of K. Now we can do the same for the peculiar velocity field. So remember, the peculiar velocity sourced by dark matter was seen in the last class. We saw this, that it's a pure it's a field which is it's curl free, so it's a pure gradient. So you can write it as minus grad of some psi velocity. So some velocity potential you can introduce, and we saw that. And even if you add some piece to this velocity which is a curl, then we saw that under cosmological evolution in linear theory, that will fall off as 1 over a. So we will assume that this velocity, peculiar velocities, they are of the form of a gradient. And we also saw that you can write a Poisson equation for this, a Poisson. So you can write del square psi. This we saw in the last class. This was given as A, H of A times F, and then you had delta X comma T. This was dark matter. We can keep that. So this F, if you remember, we defined it as D of log D, D log A. And so we want to write down a Fourier transform of this. So the convenient thing is that when this Laplacian operator is appearing in an equation, so you can immediately see that under Fourier transform, this Laplacian operator just yields a minus k squared, because each time you do a gradient, you get an ik, a factor of ik, because the ik comes from the exponential. And when you have two of them, which is a Laplacian, you have a minus k squared. So this under Fourier transform will just be minus k squared psi tilde, which is a Fourier transform of this potential. This, and this, A, H, and F, these are all functions of time, so they don't get affected. And then you have delta Fourier transform of kt. So you can immediately see that psi tilde of V will be minus AHF delta by k squared. So this is convenient. Now, of course, you want to write down not this, but the velocity. So the velocity will be the gradient of this. So if you go back to this equation, so the velocity now in Fourier space will be the gradient of this. So you get a minus ik. So an additional ik will come from this gradient times psi tilde. So this is going to give you A, H, F square. Sorry, F F pi k square ik, and then you have delta k comma t. So these are very convenient. So these results are very useful, as you will see later. And in the same way, you can take the Fourier transform of the gravitational potential. So if you remember, del square phi was 4 pi g rho bar delta a square. So you would have similarly phi tilde, which is the Fourier transform, as minus 4 pi g rho bar by k square, and you have a squared delta. So these are useful results. We shall be using these later when we go for statistics of the density field. Okay, so now let's just go back to our discussion of growth of fluctuations again. So today we shall start with fluid which has pressure support. So typically baryonic matter. So we had written the expression for the growth, the equation for growth, which was delta double dot plus 2 a dot by a delta dot equals to del square p by rho bar d square plus 4 pi g rho bar. So let us study this equation. Now we'll take into account this pressure term. And we saw that you can define a sound speed. So CS square, if you define it as del P del rho. So then you can have this this quantity, which is P, which is actually, you can write this P over here. This P over here, you can write it as CS square delta rho. So that is equals to CS square rho bar delta. So with that, this equation can be written. Now, please don't make any assumption about this CS square being something which does not change with time. There's no reason to believe it. It's in fact, for most purposes, going to be a dynamic quantity. So delta dot dot plus 2a dot by a delta dot equals to cs square by a square del square delta plus 4 pi g rho bar delta. Okay, now let's study this in a approximation. So let's first see what does this equation. So this is like a wave equation, right? So you have this double time derivative and double space derivative. This is like a damping term and this is like a source term. So this is essentially a wave equation, right? So if you bring this term to the left side, it's essentially a wave equation, except that you have it's a wave equation with a source and a damping term. Okay, now so you do expect oscillatory solutions. So let's first ignore this damping term. So first case one is when, say, you are basically in a steady universe. So a dot is 0 and say a equals to 1. So you are just not really looking at any evolution. So then what you have? Then you have delta double dot equals to c square. A is 1, so it's just del square delta. This is not cosmology. This is just a case study. 4 pi g rho bar. So it's basically interaction of a gravitating fluid with pressure support. Okay. So what happens when a fluid with pressure, which has pressure support, undergoes self gravitation? So it's basically this is what is studied under what is known as Jeans instability. So there are two things at play: gravity, which is trying to make the fluid collapse. So it's the structure, the deltas will try to grow under gravitational instability, whereas pressure is trying to oppose that, and it's trying to annul the effect of gravity. So this is a wave equation. So we can expect a plane wave kind of. We can make a ansatz. So you can take a trial solution or like a plane wave. So if we take that, so you can see that this delta, you can assume it to be some form e to the power I. Okay, k dot x minus omega t, a standard plane wave. And if you substitute it over here, this double derivative in time will give you a minus omega square, and this will give you a minus cs square, k square, plus 4 pi g rho bar. And you can immediately see that this gives you two possible values of omega, plus minus square root of cs square, k square, minus 4 pi g rho bar. So here you can clearly see that now there's a competition between the terms with cs squared, this pressure term, and gravity. So this is the gravitational source and this is the pressure term. So you can clearly see that depending on which is greater, this omega will be real or imaginary, right? So if it's real, then it corresponds to an oscillatory solution. Whereas if it's imaginary, because we took the solution to be an e to the power I omega t. So if we take the imaginary root, then omega becomes imaginary, but then the solution becomes non-oscillatory. So depending on that, so you have two possibilities. When this k is greater than square root of 4 pi g rho bar by cs, this implies oscillatory solution. And if k is less than root 4 pi g rho by cs, you get non-oscillatory. So it's like some growing, could be decaying also, but not oscillatory. So we define this quantity on the right hand side as what is called the Jeans scale. So you can define something called kj as 4 pi g rho bar by cs square root, and a corresponding Jeans length scale, which is 1 by kj. So some people use a 2 pi, but doesn't matter. So you can clearly see that now we have a physical scale at play. Now what does, and you can actually verify that this has dimensions of, k has dimensions of inverse length. So there we have a physical length scale, and you can clearly see that what it means that for a system undergoing gravitational collapse to have pressure support is that if you have this region and there is some domain, and if you're looking at scales which are larger than this xj, so if you have say scales x greater than xj, then you would have growth of structures. Whereas if you are inside, if your x is less than xj, then your solution is oscillatory. So modes which are, so the scales which are larger than the gene scales, they grow because gravity is then the dominating force at play. Whereas on smaller scales, the pressure is, if x is less than x, the pressure starts coming into play, and it sort of stops the growth, and then you have oscillatory solution. So that is the basic physics, and this is gene sensitivity. So you can see now that the role of pressure is to sort of cause this growth to get subdued, and at least on some scales you will have restricted growth because of the presence of pressure. Now, of course, if gravity dominates and pressure is completely subdominant, then you basically have a growth, right? Because that's what we studied in the last class. There is no pressure, and then you typically don't have these oscillatory suppressions. You will have basically growth of structures. It's a possibility of growth. Whereas if there is a dominant pressure term, then you would have these oscillations. And if the pressure term is really strong as compared to the gravitational term, the source term of gravity, then of course you would not have structure, because the pressure is so strong, it would always lead to oscillatory solution. So the source term can then be neglected, and then it is just damped oscillators. You would get pure oscillatory solutions. So depending on what is the dominant term in your universe, you would have different situations. Now let's now go back to, of course, this was just in a static background. So now let's actually go back to cosmology. So so if you have very subdominant pressure, so the pressure is negligible, then in cosmology we just have delta dot dot plus 2a dot by a delta dot equals to 4 pi g rho bar delta. And this we saw allows for the possibility of growth of structures, growth of fluctuations. But now let's look at the other extreme before we go to an interplay. So the other extreme is when the pressure term dominates. So let's say the pressure term is the most dominant, and you can say ignore the gravitational source. So then you have basically the equation becomes, so this is when gravity dominates. And on the other extreme, you can have this equation, plus 2a dot by a delta dot plus cs square k square by a square delta equals to 0. Now what I've done is I've actually used the plane wave and just used that, taking the Fourier transform, and actually brought this k over here. Okay, great. Because there was a Laplacian, so I took that Fourier transforms, you get a k. Now, this solution is not very easy to do because we have a time-dependent a dot by a, this Hubble parameter sitting over here. So what one can do is one can try to, of course, when this a dot by a is 0, then you have basically a pure oscillation. It's just SHM, right? So now if you just have this thing going to 0, the damping going to 0, then you have simple harmonic motion. So that's just pure sound waves. So, and you can, the thing that I want you to appreciate over here, what is the kind of frequency that we have. So this delta, that will go as e to the power I cs k by a t, right? So this is the kind of frequency that we have, right? So just to get a hang of what is the fluctuation, what is the temporal frequency of these oscillatory fields. So it's basically this CSK by A is what typically appears. Now please, this is of course assuming CS is constant, which is not necessarily the case. So if you can assume CS and all these terms to have a behavior which is time variable, which is the general case, then this equation, of course, gets far more difficult to solve. So let's retain this A dot by A. And one way to try and analytically solve this equation, of course, we don't have the gravitational source, which we shall bring right just after this. But if you have this kind of a solution, this is like a wave equation. It's like if you remember quantum mechanics, this is like a Schrodinger equation with a potential, right? Now, one way to approach this is using what is called the WKB method. So what we do is we take we make a solution as assumption for the solution delta of t, which is some A of t times e to the power minus I phi of t, where we assume that this amplitude does not vary as fast as the phase. Okay, so we assume this kind of a general form, A of t and phi of t, and then we substitute back into this equation. So if you do that, and then you will see that you get, of course, I mean, you have to differentiate, and I'm not going to go through the details of the algebra. So what you will see is you will get this equation. You will get A double dot minus 2I A dot phi dot. A and phi are both functions of time, minus I A phi double dot minus A phi dot square plus 2 A dot by A dot minus 2I A dot by A phi dot plus CS square K square by A square A. Okay, so this is equals to 0. Now here is where we are going to make some assumptions. So this is where we want some kind of an approximate. This is a exact equation till now. So now we will make an approximation, and we'll assume that, okay, let's look at this d phi dt, the variation of this phase d phi dt. So this from our first order, 0th order solution, this is something which goes as CSK by A, right? So this gives some time scale, right? So this gives some kind of a time scale. And at the same time, you have 1 by A dA dt. This gives another time scale. And this t is basically the expansion time, right? So what we shall assume is that this oscillation frequency, so we'll assume that this t is much, much less than t. Or in other words, the oscillation expansion is actually, the expansion time scale is much, much larger than the oscillation time scale. So with that, there would be a lot of simplification. We can drop all the terms which involves the second derivative, the derivatives of A. So all these derivatives of A we can drop. We'll assume that this this particular time scale t is much, much less than the time scale of expansion. So very good. So once we do that, so we will ignore all A double dot and A dot terms. And what we shall have is, I'm just going to quickly do the algebra. So once you do that simplification, you will get two things. You will get phi dot square will be CS square K square by A square. And then you will, this is the first order, you should have next terms. And then you have the other equation. After ignoring all this, put all these to 0. So you would have A phi double dot plus 2A phi dot A dot by A plus 2A dot phi dot equals to 0. And this, after some simplification, you can basically write this as ddt of phi dot A square and equals to 0. So you immediately have this phi dot A square equals to a constant. So you get phi dot equals to 1 by A square, I mean order of some constant K by. So so basically what you have is amplitude goes as 1 by square root of phi dot times A square, right? and therefore you can write down your solution now, delta. Remember, delta was a to the power I phi, and phi dot we already know. Phi dot is CSK by A. So delta will be proportional to up to a normalization 1 by square root of CS A e to the power minus I integral CS K dt by A. So we have integrated this equation to get this way. So this is like a WKB solution to the problems, but the thing to understand is the CSK by A is what appears as the frequency, and that is just something which you should appreciate. Now, the thing is that this CS is in most general cases a function of time, as we shall see. Okay, good. So here we have ignored the source term, the gravity. So it is a pure oscillatory solution, as you can see. There is no chance of any structures because there is no gravity. So there is no instability due to gravity. So now let's take the full equation.
There is one question in the chat box.
Yeah.
Is delta is a function of k by Prasun Datta instead of x?
Yeah. It's a function of k. We have introduced this k, no? So we have actually everything else is a function of time. So our equation, if we just take the Fourier transform, or we substitute the wave e to the power I kx, so that k will come. Yeah. So for a given k, so this is delta. For a given k, the time dependence is given by this. Okay. So I should have probably written the capital delta, but anyway, this is self-evident. Good. Okay, now let's go back to our full equation. So, and let's now actually talk about baryons. So for baryons, we have delta baryons double dot plus twice A dot by A delta baryon minus 1 by rho baryon bar, A square del square P equals to, now we have the source, but the source is now G rho bar dark matter delta dark matter, and this is something which we had said. So it's so the growth is sort of propelled by dark matter, but this pressure term is something which is coming from the baryonic fluctuations. Okay, good. So this right hand side, first of all, we can write down if you introduce the omega, the density parameter. So then you can just write this in a different way: 380 squared by 2 omega matter 0 delta dark matter by AQ. Okay. So now what we do is we write it down in Fourier space. So this is just time derivative, so there's no problems. You can have delta baryon dot dot. Now it's a function of k, so it's a kt plus twice A dot by A delta baryon dot minus, now this del square P will give you a k square. And if you remember this, you could write this P in terms of the sound speed. So you can write CS square, and then rho bar will cancel, rho bar CS square. So this by A square, you have delta B again, and that is equals to 3 by 2 H naught square omega matter naught delta dark matter by AQ. So this is the equation that we have. Now this is typically a very tough equation to solve because you need to now understand the CS. And so you need some kind of an equation of state, some kind of a behavior, some kind of understanding of your baryonic fluid and how its pressure density relationship works. And typically you will have some astrophysical inputs to model this CS, and it would require either some sort of a temperature you introduce, and the temperature will have its own evolution. And you could have, for example, an ideal gas simplification, or you could take some, so you could have lots of modeling. So the thing to understand is that the CS square, which is a function of time in general, is something which you need to model from astrophysics. That depends on the temperature. And so it's basically a thermodynamic quantity, pressure, density, all these thermodynamics of the gas, all of which are functions of time. Okay. So this term is something which you really need to worry about. And that's the crucial difference from dark matter. So that is what makes all the difference. I think I have to put a plus sign when I take the Laplacian, right? So minus k squared. Okay, good. So now it turns out that I can rewrite this. Now I can introduce this co-moving gene scale. Now remember, this xj was CS by root 4 pi g rho bar, right? So what we do is we introduce the co-moving. So this is, so we can introduce, so we can just divide it by a, and you call this xj, okay? Now what we want to do is we want to write this term, the second term over here, in terms of this pressure term, okay? So this is baryonic now. So what will happen is, with this definition, it's very easy to see that of course this k square will remain, this cs square. So you can write cs square by a square as just xj squared times 4 pi g rho. So let me write that down anyway. So delta baryon dot dot plus twice a dot by a delta baryon dot plus k square. The cs square by a square will be 4 pi g rho bar. This a squared cancels, and then you have delta baryon, right? By a cube. Should I take this a? Let me just check what is happening. Cs square by a square is right. So here there would be no a. So yeah, so I think it will just be so this will be exactly this term. So this will be plus yeah, let me just write it. So I convert that omega, so it is exactly this term, no, 4 pi g rho bar d del time. Instead of del time, you will have 4 pi g rho bar baryon delta baryon, and then you have k square, right? So this you can write as, okay, rho baryon 0 by a cube. Again, you can introduce and convert it using the critical density into an omega. And on this side you have 3 by 2 h naught square omega matrix. Here you have xj square. Great. So just verify this, okay? So I've introduced with this definition, you will get this. Perfect. So what you have now is basically this term and this term looks exactly the same except for a factor. So delta baryon with this substitution, okay? And this is the definition of the gene scale. Plus 2a dot by a delta baryon dot plus k square xj square. Then you have this factor, which is exactly the same as this. You can write it as 3 by 2 h naught square omega so this, okay, I'm sorry, I should actually, I'm wrong. This is not omega baryon. This is rho. Because this is the gravitational source term. I should not put, so the gravitational source term always will have dark matter. So this is always dark matter, sorry. So this is still omega matter, dark matter. And on this side, you have 3 by 2 h0 square omega matter, delta dark matter by h. Okay. And this is also in Fourier space. So I should also probably use capital delta. So right, capital delta dark matter. Right. So, okay, crucial thing. So the xj, this lower term, this term which comes from gravity will be always be sourced by dark matter. So I should not have, I'm sorry for that. I should not have put baryons there. The CS is something which has got to do with the baryonic physics, right? So here you will still get this omega matter, the dark matter density parameter. And so we have introduced this xj. So this omega Is omega dark matter, sorry.
Another questions by Fazlu. A to the
Yeah,
power A to the power cube is there in the third term of LHS.
where?
In third term of LHS,
Here in this question, yes.
A cube term.
There will be an a cube term, which rho bar is 0 by a cube.
You go to the last equation.
Yeah, there will be an a cube term. It's exactly because I have to write rho bar as rho bar. One is that ca square by a square, that has been taken care of, but rho bar has to be written as rho bar 0 by a cube. So this a cube comes from there. This rho bar dark matter has to be written as rho bar 0 present by a cube. So that is from where this is coming from.
Okay. It is not because the cancellation is already taken care
Cancellation
of,
is already done. Yeah.
Okay, then it is clear.
That's the, yeah. So this is coming from, I'm written say 0. So
Okay.
this is rho bar dark matter, which is a function of A. This xj is a function of A. So it's a time dependent quantity, right? So now I'm writing in terms of omega matter present. So that's why I need an extra
Okay,
one
there
by
is an a cube. Yeah. Fine,
okay.
clear.
Is it everything clear now?
Yes, it's clear.
Okay, good. So now you see the moment we introduce the gene scale, this term and this term are exactly the same, which makes which makes some allowance for some convenient solution, except that this xj I've written, but xj is a horrendous function. I'm just calling it some xj is not going to solve our equation. It's a function of A. So, I mean, I'm going to write this very clearly. Xj is a function of A. So it depends on, for example, it will depend on temperature and things like that. You would have to take some kind of equation of state. For example, it will depend on CS and all that. So if you take pressure to be some rho to the power gamma, some kind of an adiabatic equation of state, or use some, and then use, say, an ideal gas equation, NKT, and all that, there will be, you can introduce a temperature and write this whole thing in terms of temperature and things like that, and mass of a proton and things like that. We are talking about hydrogen, basically. So this xj you can immediately see will depend on A, right? But if it make an assumption, of course it's a ridiculous assumption, and therefore this won't work. But if we make an assumption that, let's assume that this xj is time independent, somehow there's a conspiracy between all these factors, and it somehow is a time, which is of course a ridiculous approximation. It's not. So you have to really solve this equation numerically. And in fact, if you could solve this perfectly with all the physics put in, everything would be solved, right? I mean, then that we have all the H1 physics. But unfortunately, that's not so easy, this evolution, because we have to, a lot of, the thermodynamics is not so very well known. So you have to model something for the gas. Okay, but let's assume, I mean, okay, in this, just to get some hang of what kind of statements we can make from this equation, let's assume that this xj is a constant, it does not evolve with time. Okay, it's just a brute assumption. Now, if that is the case, then this term does not appear. This k square, xj square just appears as a constant, right? And then you see this, since this is baryon and this is dark matter, and the same factor is sitting on both of them, you can immediately see that if you take this to the other side, you can actually get a solution. So you can get a solution delta baryon, which is proportional to the delta dark. So this is like something which we call the biased, so the gas follows the over density of dark matter, and that is under this assumption. So then this is a solution, and you can actually verify. You can substitute this. The denominator is a constant, right? Because now xj is a constant for a given k. So if you substitute, what will you get? You will get the first term will be delta dark matter by 1 plus xj square k square, and then second term will be twice h delta dark matter by 1 plus xj square k square. This term will be k square xj square by 1 plus xj square k square. This factor 380 whatever a cube omega matter, and then you have dark matter, and on the right side you have 3 by 2 H naught square AQ omega matter dark matter. Now you know the dark matter satisfy this its own equation. So that term, if you see, you will see this is consistent because you multiply the whole thing by 1 plus xj square k square. You will see you get the equation for the dark matter over density. This cancels, you get exactly what you expect. So, so the point is, this is true. So this solution is a good solution, but that is under the assumption, of course, that xj is a constant in time. But we can get some insight from this, right? The first thing to note is that if you look at this behavior, delta baryon is delta dark matter divided by some 1 plus xj square k square for a given k. So everything is for a given k. You can immediately see that the behavior is when you can have this xj k much less than 1, right? So much greater than 1. So then this delta baryon will be basically delta dark matter. You can ignore this. So you will have just xj square k square, right? And so this dark matter is basically, sorry, I'm written the, this is dark matter now. So this dark matter, we know this is basically from the Poisson equation, this is basically del square phi. I'm proportionately, I'm writing up just to see what kind of scalings we have. This is proportional to del square phi. So in Fourier space, this is k square. So 1 by k square. So this basically means this delta m by k, dark matter by k square. This is basically phi tilde. So basically a minus phi tilde. It's minus k square. So it's actually perfect because on these scales, so you are essentially saying that xj is much greater than 1 by k, or rather let's put it k, because we want to speak in terms of k. K is much greater than 1 by xj. So we are looking at very large k's, which essentially means we are looking at very small scales. So over there you can immediately see that this baryonic fluctuation is essentially following the potentials, and these potentials are created by dark matter. So that's what you have heard, right? So dark matter creates potential wells, and the baryons sort of fall into these potential wells, and that is what we see. And in general, you will see that, of course, this delta baryon will be less than the dark matter fluctuations. The baryonic fluctuations will be smaller by some number. It's because this is a positive number, so this is going to be greater than 1, and this is going to be smaller. So fluctuations, and on, of course, when this term is subdominant on very large scales, delta baryon is just equals to delta dark matter, so it just follows the dark matter. So on very large scales, baryons follows the dark matter. On very small scales, what is happening that the baryons, the dark matters create potential wells, and these baryons then sit at the bottom of those potential wells. So so this much physics we can understand, which is what you know, and now we have good mathematical reason to believe. But of course, I mean, one has to numerically integrate these equations and in a self-consistent manner, because this xj itself has its own evolution equation. So those have to be coupled with it, and it would lead to a lot of coupled equations, which has to be dealt with numerically. And of course, in reionization, this becomes even more complex because of how the gas evolves. Okay, good. So much about Jean's instability. How much time do we have? Okay, so I think the next thing that I want to go into is actually studying this delta k, or basically delta x. So these are Fourier transforms of each other. So till this while, we have been predominantly interested in time evolution. So we have looked at how density fluctuations vary with time, how they evolve in time, and that we saw for the case of pure dark matter. And now today we saw that even if you have baryons, you can make some statement about how baryonic fluctuations grow in time. And we saw there are other cases. For example, if you have a predominantly pressured term, then what kind of oscillatory time evolution you would have for fluctuations. Now, there was one comment about dark energy yesterday. So please understand, in our entire analysis, we are not doing a kind of cosmology where we are allowing the dark energy to have fluctuations. So dark energy has no fluctuation in our theory. So it has pressure, but the pressure or the density, they are constant. So there are no fluctuations in dark energy. So please remember that these equations that we have written, they all involve fluctuations. The P that I have written is actually fluctuations in the pressure. The delta we have written is the fluctuations in the density. So we have no fluctuation equation for dark energy. So how do the dark energy enter into this entire picture? It enters through A of t, which is going to be dependent on the cosmology, and therefore will be related to which will of course be sensitive to what kind of dark energy you put. But since we are not considering dark energy to be something which is clustering or has fluctuations also, they don't appear in the equations of the perturbations, right? So that's something which I want to mention. So I think I will stop now because I want to start a new topic in the next class. So where we will now start looking at the nature of the spatial variation of the fluctuations, and we shall enter and then we'll talk about statistics of the perturbation quantities. So I think I'll stop here and take questions.
Yes, so please use the raise hand button or the chat option to ask questions, please. Yeah. Olgodeep.
Hello, am I audible?
Yeah.
Okay, sir. So I just have missed the relation between the fluctuation of baryons and the fluctuation of dark matter. So can you please repeat it once again? Like
Okay.
You have mentioned that x square kj square very greater than 1 defines something. So I just
Okay. No. So okay, did you get to the equation at least how we obtain this equation?
Yeah. Just the
And
last
then
case.
and then we when we saw that when the baryonic when the gene scale is something which you can hold constant, then you can have this, as I said, this you can just verify, very easy to verify because this is a constant, right? So you can immediately see the exact same factors appearing on both sides. So you can just take a proportionality, and that proportionality will nothing but this. So this solution is very easy. You can just substitute, and I just showed you. So the baryonic fluctuations, and we are working in k space for a given k, is basically this dark matter fluctuations divided by this factor. Now this factor of course is sensitive to the scale because it has a k sitting over there, right? So we have to talk about what is the relationship between baryonic fluctuations and dark matter fluctuations on different scales. Now on very large scales, when k is very small, now the scale, as we shall see in the afternoon's class, that the scale is inversely related to the k, right? Because k is like a 1 by distance. So
Yeah.
so when we have very large scales, this k is very small. So this xj square k square term they don't contribute. So delta B is basically roughly just related to dark, which follows dark matter. So the fluctuations of the baryonic fluid basically follows the dark matter fluctuation. So they're just same. I mean, you could have some bias maybe, but they're just related to one another. But of course, when you have the other case, when you have very small scales, so on large scales, baryons follow dark matter. So this is something which you have heard. I mean, in 21 centimeter cosmology, that is something which leads to a lot of simplification, right? The gas follows the dark matter distribution on large scales. And that's something which we can at least heuristically get from here. On small scales, of course, it is wrong to use this because this xj square will now, I mean, the physics of xj, of the genes process has to be brought in. But at least in this analysis, we can immediately see that, okay, on very small scales, this xj square k square, the k is very large now. So the 1 can be dropped, and you have delta B is then delta dark matter by, so this is small scale. On small scales, you have delta B equals to delta dark matter by k square, right? Delta dark matter by k square. Now, delta dark matter by k square is basically the gravitational potential, right? Because if you remember, the Poisson equation gives you del square phi equals to delta dark matter. So in Fourier space, this is just minus k square, right? Minus k square phi equals to delta dark matter. So this you get minus. So this minus sign comes. So it's basically this delta baryon is proportional to negative of the gravitational potential. So what it essentially saying that on these small scales, the way to visualize is the following, that dark matters create gravitational potentials. So the dominant thing that is there are the dark matters which create gravitational potentials, and the gravitational potentials make so the baryonic field is basically going to follow these the places where these gravitational potentials are. So if there is an overdensity of gravitational, if there is a peak, if there's a positive potential, then there will be negative. So the baryons would avoid that region. So baryons would sort of sit at the base of these potential widths. So that is the picture that we get. Of course, it's a very schematic heuristic picture because we are not really taking into account any of the astrophysics and the time dependence of various quantities, but we get a rough understanding of what's going on. Does it answer your question? I'm not sure if I answered your question.
Hello. So I understand the thing. So that means for the larger scale, the baryons are actually so it behaves like the dark matter pattern. But
It doesn't behave; it follows. So
it follows. It follows. Actually, yeah.
So there is a dark
follows.
matter. So there's a dark matter distribution, right? Which is
yeah.
So what does the dark matter distribution do? The dark matter distribution is going to create potentials.
Yeah.
So wherever, the baryonic matter will just follow the dark matter. Wherever there is dark matter, you see there is going to be.
Yeah. So and for the smaller scales, so this is basically the scaling relation, the baryon fluctuation.
So you see that the baryonic fluctuations basically follow the gravitational potentials there. You get delta dm by k square. So then it's basically a tracer of the potential widths.
Yeah.
So that's all. That's the. I mean, I don't want to. Go beyond this very simplistic statement, but because it's not accurate, no. I mean, it has a lot more to it. Analytically, this is what we can sort of figure out. And in fact, the rest of this school, you will learn a lot about H1, right? So you have to do numerical simulations basically, because one doesn't know really. I mean, where the gas is. I mean, if you knew the gas distribution, your problem would be solved. But we don't know. So we have some idea about dark matter because we can do some dark matter simulations. But how do we model the neutral hydrogen? How do we distribute the gas? So that's where you have to put in a lot of modeling, right?
Yeah. Okay. Thank you.
Yeah. So that's the whole richness of the subject. I mean, this is a very, very pristine, very sort of sterilized version, but the real physics is far more complex. Far more complex.
Sure. Thank you.
Any other question?
Can't see any others raise hand option.
Okay.
Please, if you have any questions, please ask. Devmallu Mukhopadhyay.
Tapo, am I audible?
Yes.
All the since right now I do not have, or we do not have the writings, your writings, only have this kind of live classes. That's why I'm asking that if the previous book about the physical cosmology is sufficient to get all those
structure
things?
Formation. This is from structure formation, the book on structure formation.
Okay.
Peebles has a book on physical cosmology. The other book is on structure formation. This is, some of these derivations are actually from that book.
Okay. Thank you.
But that is, So that most of this stuff is there in that book.
Okay. Hope you will upload all those things very soon.
Yeah, so I'm trying to write these down and scan and send it to the organizers so that you will have access to these texts also.
Thank you.
Shubhadeep has any question? No.
Please go ahead. I don't see any other questions. So if you have any questions, please ask. Unmute yourself and you can ask. Okay, I think there are no questions. Let's
Okay.
stop.
So we'll meet at 2:30.
Yeah, so we'll meet again.